Okay, last unit. Kind of relates to unit 3 when we talked about the relationship between two quantitative variables, but it involves testing. So the first thing we're going to look at is something called a chi-square test for goodness of fit. So the example we're going to use is in 2014, Harvard was sued by a group of Asian American applicants who were rejected in admissions, and they claimed that there was racial discrimination. And in 2018, the courts released reports on Harvard admissions data, which is something because these elite private schools in the States don't release data like to the public. But because it was in the courts, they had to. So people got kind of an inside look as to some of the numbers. And in 2023, the Supreme Court considered the case and did find evidence of discrimination. And so it overturned the use of race-conscious admissions at most universities. Okay, so here's the data. And the question is, was there convincing evidence that Harvard discriminated against Asian applicants? Okay, and you can see here what we're likely going to do, because we see the phrase convincing evidence, which suggests some sort of test. Okay. So here's the data from 2019. Okay. Here are all the applicants, of which there are many. And the top 10% is broken down by group. So we can see that Asian American was over 50% in the top 10% of the applicants. Hispanic was 3.1, African American was a little less than 1, white was about 39, a little less than 40. But when they admitted all the students and then broke down by race, this is what happened. So even though more than half the applicants in the top 10% were Asian American, only 21.4% were admitted out of the entire class. Hispanic was higher, African American was higher, white was higher. So you can see the case that Asian Americans had to bring to go to the courts to say, no, this is unfair. Okay. So just by looking at the data, again, like we always do, we sort of look at it and say, boy, that seems to suggest that, yeah, there was discrimination against Asian Americans that were applying to Harvard. But we want to be more statistically sound, okay? So imagine Harvard claims we only accept top applicants, we treat those applicants equally. Our admitted class is as good as a random sample. So what they're saying by that is, if this is the applicant pool breakdown by race, then their admitted students will be approximately the same percentage breakdowns, which clearly we see isn't the case. Okay, so we would like to test if there's convincing evidence against this claim. Would it be, now one thing that we could do from what we know so far is we could do 4 Z-tests for proportions, okay, with each group, and then see if there was convincing evidence, okay? But there's a problem with that. And the problem, like I said here, or up here, multiple tests. If you remember when we were talking about the power of tests and type 1 and type 2 errors, if you do a whole bunch of tests, okay, remember, every time you do a hypothesis test, if the significance level is 5%, that means you got a 5% chance of making an error, specifically a type 1 error. You got a 5% chance of getting it wrong. Okay. So the more tests you do, the chances become that one of those tests is going to be wrong. So that's why we want to try and avoid multiple tests and come up with something different. Okay. So would it be appropriate? No. First, it would be time consuming and possibly costly if you're hiring someone to do it. But more importantly, second, multiple tests increase the chance of making a type 1 error. That's when we reject the null, but we shouldn't have. Okay? Which means one of our tests could be wrong. Whereas if we did one test that included all the data, right, it reduces the probability of getting it wrong. So therefore, instead, what we're going to do is something called the chi-square test for goodness of fit. And we still break it down by hypotheses, a null and an alternative. So remember the null, which is the default, or sometimes called the dull. It's the status quo. There's no discrimination, racial discrimination, so the distribution of admitted students is the same or matches the population of top applicants, the top 10%. So it's the same as the claim distribution. That's what Harvard's claim. Okay. But we want to test the alternative, that it's not the same. There is a difference. And again, the alternative, and oftentimes we refer to it as the research hypothesis, because it's what we're doing research on to see if it exists. Okay. And this does not match the population of top applicants. So, just like we were doing with hypothesis tests with proportions and means, whether it was one sample or two sample, we started by assuming the null was true. Okay? And what that means is Harvard's admission process admissions process is similar to randomly selecting distribution of top applicants. Which I've already explained. It's all good. What Harvard says, it's all true. So I'll let the no is in fact true. How likely is the data you have gathered? Okay. What does that suggest? So what we need to do is we need to compare the actual distribution, and by distribution I mean race of the students that were admitted, or we'll just call them admits. So we compare the actual to the population distribution of applicants. We see, is it similar? Is it not? Okay. So how likely, what's the probability that we got the results that we did? So that's why we compare. And then we draw a conclusion, like we always do from a hypothesis test. If there is a difference, admits are not representative of the population distribution. Hypothesis test. How likely is it we got the results that we did? What's the probability? If we did this over and over again, was this just a weird year? Or if we randomly sampled many years, would we see some kind of difference there of the population distribution of top applicants? So here's how you go about doing that. Once again, there is a longer way, and then there's a shorter way where your graphing calculator does the work for you. Okay? So the longer way is to calculate what is called the chi-squared statistic. Okay? So the sample size we have is the number of admitted students, which was 2023 for the class of 2019. How many would we expect to admit if it's a random sample? So remember, this is the population distribution of top applicants. So that means to find each one, we would have to find 57.5% of 2023, 57.5%, or sorry, 0.031% of 2023, 0.08% of 2023, and 38.7% of 2023. That should give us an appropriate breakdown of admits, what we would expect according to the population distribution. So if I go to 1 decimal place for each, I get 1163.2, 62.7, 16.2, and 782.9. But then we go to the data and see, okay, what actually happened? What were the observed admits or observed counts? So we're just going to take these 4 numbers, put them here. We would have expected 1163.2. We would have expected 62.7. We would have expected 16.2. And we would have expected 782.9. But these are the ones we actually got from the admits data. Okay. So to calculate the chi-squared statistic, we are going to do our observed count minus the expected count, okay, because we want to find the difference between the two. We want to square it, because if we're going to add them all together, if we don't square it, positives and negatives will cancel each other out, and it'll be a useless result. Okay. And then we want to divide it by the expected to scale it. So what I just said here, all right here, so we want to compare what we actually observed to what we expected. And that's under the null hypothesis. So that's why we subtract the two. Like I said, we square the differences to get rid of negatives. Much like we did when we first learned standard deviation in Unit 1. We subtracted, like for each data value, we subtracted the data value by the mean, and then we squared it. Because if we didn't square it and added them all together, they just cancel each other out, like I said. Okay? So do not cancel out. When we add all the differences. It's so crazy. And then we do this to scale the differences by what we expect. So for the first one, for the Asian American group, we would do 432 minus 1163.2. Square that, divided by 1163.2. And we would get approximately 459.6. We do that for each one of them. We add them all up, and that's our chi-squared statistic. So for this one, if you do it the same way, you're going to get 541.7. For this one, you're going to get 2717.0. And for this one, you're going to get 143.4. Okay. So to find the actual chi-squared statistic, like I said, it's the sum of all those numbers. It's the sum. So I calculate each one using this formula, and then I add them all up. This is a formula you will get. You do not have to memorize it. Okay? So if we add it all up, it's going to be it's going to be 459.6 plus 541.7 plus 2717.0 plus 143.4, and that will give us 3,861.7. Great. So what does it mean? Well, here's what it means. When it's a large number, okay, that means that your observed data is very different from what you observed. Sorry, from what you expected. Okay? If we converted that to a p-value, that means, remember, it would be a low p-value. The probability of getting the results that we did from the sample is very low. So we reject HO and we say, yeah, there is convincing evidence of discrimination. If the chi-square is small, it's the opposite. So that means that your observed data is very similar. It's not different. So it has a higher p-value, which means we don't reject. We don't reject HO, or we fail to reject HO. Remember, we never say we accept HO, because HO is what is assumed to be true. So that's doing it the long way, and you can see that the more groups you would have in a situation, that would take quite a bit of time. Okay? So we have a shorter way. And once again, it's the four-step process. Okay? So here's just a refresher at all of our data. And the question is, do the data below provide convincing evidence at the 0.05 significance level to refute Harvard's claim? Okay? Well, state. This is where we state the two hypotheses. So HO and HA. Racial distribution of admits, those who are admitted. Is the same as the claim distribution. Racial discriminate, the alternative, racial distribution of admits. Remember, we're not saying it's less than or greater than, we're saying that it's not the same. Of admits is not the same. That's the claim distribution. Notice we didn't define a variable, so we don't have to write where such and such represents the true. Okay, we didn't do that in this case, so all we have to do for a chi-square test is write these two. The plan, well, conduct a chi-square test for goodness of fit And then it's the same conditions, except one little change. Okay? So random again. So random, 10%. And like proportions, large counts, not large sample. So remember, we're going to assume that the students were randomly selected from the group of top applicants. Okay? Assume, otherwise we can't proceed. Admins were randomly selected. From pool of top applicants. It's 2023. Yeah, less than 10% of all top applicants. Well, again, there are a lot of applicants, not so many in the top 10%, but again, we have to assume. Okay? We're not entirely sure about this, so we want to proceed with caution. Okay, but we're going to assume. And the large counts. Well, that's when we find all of those percentages when we did 0.575 or 57.5% of 2023. And we got 1163.2. And then we did the, I believe it was Hispanic, yep, 0.031 of 2023. And we got 62.7. And then we did African American, which was 0.08 of 2023, which works out to 16.2. And then we did white, which was 38.7% of 2023, which was 782.9. Not as strict as proportions. These have to be greater than or equal to 5, not 10. For a chi-squared test, it's 5. For reasons we won't go into here. Okay. So just keep that in mind. That's a slight difference from the large counts for proportions. Okay. So we're going to say good, good, and good, which means we can proceed. So now we're at the do phase. And the do phase does take some more work. Okay. And we're going to use our graphing calculator, but we have to enter all the data. Okay. We have to enter the expected data and the observed data. So we've got to enter 2 lists of 4. Do you remember how to enter a list? It's been a while. So go to stats and then don't scroll anywhere. It'll say edit. Just go there and you should have your lists. Now, if you've already got some numbers in there, you can clear them out by highlighting L1, press clear, equals, and it should remove the list. Okay? And then for L2, L3. So for L1, make sure I got the right list here. We entered the observed. Okay. Because remember, when we do our calculation, it's observed minus expected. So we're going to enter 432, 247, 226, 1118, and then we're going to scroll over to list 2, and we're going to enter the expected, which is all those values on the previous page that we did under large counts, or that we did on the page before that. So it was 1163.2, and then 62.7, 16.2, 782.9, and we've got our list done. Okay. So now what we want to do is go stat again, and then go to the tests. And this time we're looking for the chi-squared, which is the funky X. And I believe, yeah, it's at D, not chi-squared test, sorry, chi-squared goodness of fit, GOF. So once you enter that, it's going to ask, okay, where is the observed data coming from? It should say L1. Where's the expected data coming from? It should say L2. What are the degrees of freedom? The degrees of freedom will be the number of groups you are entering minus 1. So we are entering 4 groups. So the degrees of freedom will be 3. And then calculate. And notice we got a number very similar for chi-square that we did when we did it the long way, right? But notice even more important below is the p-value. What's the probability of getting a result like this, assuming the null is nothing, 0, which suggests big time there's a difference. Okay, so just to summarize this, this is how I would show my calculator work. So under the do phase, let's say, okay, I'm gonna L1, I'm gonna enter these. L2, I'm gonna enter these. I'm doing a chi-square goodness of fit test. And under that, my observed data is going to be from L1. My expected data comes from L2. And you don't have to write the chi-square statistic unless you're asked. We're focused on the p-value. So when it says p, it really means p-value equals 0. We already calculated the chi-square statistic alone. And then we conclude. And it's the same conclusion as when we did tests before. Because our p-value is less than our alpha value, we reject HO. We have convincing evidence, da, 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 da. So because our p-value is 0 is less than our alpha value, so it's 0.05, we reject. Reject. Jump. we have convincing evidence. And then you just rephrase, and then you just restating the question again. So we have convincing evidence. Racial distribution of admits. Exceptions. Now, if we talk about this. I'm not sure whether this was used in the court's decision or not, but it wouldn't hurt. Do a statistical study on it to see how likely is it. But I wouldn't be surprised if something to this effect was presented to the courts, which caused them to overturn the decision, say that it was racial discrimination. Okay?